So our next speaker is here from batting from the home team, Greg Howland from RIT. He'll be speaking to us about efficiently certifying large amounts of entanglement in high-dimensional quantum systems.
Thank you. So I'm, much like Andy, going to be also talking about high-dimensional entanglement. Let's see, what's our pointer situation here? Is it the... doesn't matter. So I'm here at RIT and Stefan Prebel's group. But the stuff I'm going to be talking to you today about, I actually did when I was at, this middle thing. What did I do? Oh, okay. Where's the laser? Oh, there it is. When I was at the Air Force Research Laboratory about a year ago with these fine gentlemen who many of you know. And I want to just especially point out that James Schneelock, who's sitting up in the center here, was responsible for basically almost all of the theory I'm going to talk about today. So if you have questions about that, he's a good person to direct those questions to. Okay, so there's a sort of big picture. Where is what I'm going to talk about fit in? We've heard a lot of nice talks these past few days about things sort of down in this platform layer. We're finally realizing these actual sort of large-scale quantum technologies in different platforms. And then you also have sort of this more traditional logical layer. That's all these things like algorithms and sensing protocols, protocols for communicating, et cetera. And as we sort of move forward and start realizing practical quantum technologies, there's going to be a need to do a lot of stuff in the middle layer, right? So these platforms have some quantum resources associated with them. We need tools that can characterize those resources and expose them up to the logical layer to the user who doesn't really want to have to worry about specifics, right, of the platform. They just want to know I have so many qubits, or I have so many qubits, et cetera, I can do certain operations. So platforms are varied and imperfect, right? None of our implementations are perfect, so we might need 20 qubits that are imperfect to realize one logical qubit or something like that. And yes, we need these practical tools. And you saw that in the last talk as well. Okay, so I want to tell you what do I mean when I talk about entanglement in high dimensions. For the purposes of this talk, we're going to have some quantum system coming from a source, and we're going to split it into two parties. And in the future, we'd like to have more than two parties, but that's what we're going to talk about for now. And high dimensional means that each party has a lot of possible local measurement outcomes. So a qubit would only be 2, but we want to start thinking about 100 or 1,000 or 512 squared, as maybe we'll see later. So if you want to measure a joint distribution of those observables, you have to do n squared measurements just to measure that distribution, so it scales really poorly. And also we might have continuous variables, like, say, a position. A particle could take any position. Or we might have discrete observables, so maybe we have many waveguides on a photonic chip. So here's some examples. Photon pairs entangled in spatial variables. Many of you probably know energy time, or time bins and frequency bins we just heard about. Path entanglement. Or maybe you even have an atomic system that you sort of divide and you partition into two parts to reason about it. Or you could have two separate atomic systems, trapped ions over here, trapped ions over here, fibers or something connecting them. So when I talk about quantifying entanglement, really what I want to know is how many E-bits, how many entangled bits I have. So you can understand an E-bit to be sort of a logical amount of entanglement equivalent to the amount of entanglement a perfect Bell state has, so 2 perfectly entangled qubits. So if I tell you, oh, my quantum system has 7 E-bits, you can think of that as if I gave you 7 perfectly correlated Bell states. There are different kinds of entanglement monotones or measures that use E-bits as their, give you E-bits, but really just think about Bell pairs. There are some other people who like to think a lot about entanglement dimensionality. I'm not going to talk about that so much today, but that's just how many entangled modes you have instead, so like your Schmidt rank. So because it's so hard to characterize these systems, you have to do so many measurements, right? in the past, we've really only been able to witness, for the most part, witness entanglement, meaning you do some measurements on your system and you get a yes, I have entanglement, or a no, I don't. But more recently, we're starting to have what are called quantitative entanglement witnesses, which you give them some measurements that you took, and they can maybe give you a lower bound to how many EBITs you have. And hopefully, you don't have to do a tomography. So sort of restating that slide, there's a hard way to quantify entanglement. Do a full unbiased quantum tomography in your laboratory. It's hard enough in these large dimensions. And then once you've done that, you get the nice task of computing one of these entanglement monotones, which is NP-hard in general. So hopefully, we can come up with an easier way. So invent a quantitative entanglement witness that has some nice properties. It might work with very limited data. That's necessary. We need our measurements to be easy and smart, so that's kind of like I'm told how trade wars are. We want our results not to be contingent on any assumptions we might make about our system. We want to do easy and error analysis, and sort of going along with these, you want to try to avoid any kind of intense computational aspects that you might have. Okay, so we want to build this thing up. So where are we going to start? Uncertainty relations are of course, very closely related to entanglement, so that's where we're going to start. So everyone's familiar with the good old variance-based uncertainty relation. But it's worth remembering that variance is a sort of indirect measure of uncertainty, right? It captures localization or clustering. So if you sort of have this dartboard and there's these 3 darts, right, the variance is actually quite large even though you really only had these 3 locations of interest. So what we've been doing for quite a long time is instead using entropic or information-based measures of uncertainty. So you can instead cast your uncertainty principle in terms of the Shannon entropy, which is a nice because that's your bits, right? And that captures the number of questions you have to ask to learn something about your system, right? To specify it, which is a much more direct measure of uncertainty. More questions, you are less certain. And I like this thinking about the uncertainty principle this way. The more information a measurement tells you about the position statistics, the less information a subsequent measurement can tell you about the momentum statistics. And just in general, if you're thinking about things in this information-based way, your measurements are sort of like questions. You can think about asking your system questions, and that's maybe in contrast with what we often naturally do, which is think about sampling some signal at regular intervals, which is a little more restrictive. I like to think you can be a little more creative this way. Okay, so how are we going to get to entanglement? Well, we have the EPR paradox, which is seen here. So that's if your conditional variances are smaller than in 2 incompatible observables, this conditional uncertainty product is small, then you're witnessing the EPR paradox, right? So if you make measurements if Bob makes a position measurement on his system and then means he knows a lot, that's well correlated with Alice's position measurement, this term is small, and same for momentum. So we can recast this entropically. So we're going to replace these conditional variances with conditional entropies. So now the way to think about it is if Bob, say, gets a certain position outcome, how many extra questions would he have to ask to know Alice's position outcome? And this is really good work done by James Schneelock way back in 2013 when we were in John Howell's lab at the University of Rochester. And if this term on the left, so this thing is a constant that we don't need to worry too much about. It comes from the uncertainty relations and also from what size your, say, pixels are. If that thing's greater than 0, you witness the EPR paradox. But it also, we found it bounded a secret key rate. And that should be sort of suggestive that you can actually go from EPR all the way to EBITs. So this is a paper we had earlier this year in April 2018. This is really all James's work. He should get the credit. So what do you measure? you measure conditional entropy and position, conditional entropy and momentum, and that can be related to the quantum conditional entropy, which in turn can bound your EBITs. So what's the point? The point is we don't have to do tomographies anymore, which is very good. We only have to measure joint probability distributions in two incompatible observables. But even that, in these large dimensional systems, is still a lot of measurements. So how do we do better? How do we use fewer measurements? So these are some semi-provocative statements, I guess, that I put on here. So first is, I like this quote, "One can regard the possibility of digital compression as a failure of sensor design if it is possible to compress measured data. Maybe we took too many measurements." Or alternatively, how can we measure just the important part of a signal, or go analog to information, or sample at the information rate instead of the Nyquist rate? And sort of what I really like are what are the right questions we should be asking our system. Okay, so you want to characterize some quantum system. It's probably not the case that you don't know anything about it to begin with, right? For one thing, if you're looking for entanglement, you probably expect it to be there. And structure sort of equals compression. So what are some things we might know? We might sort of have some abstract quantum-y things we expect, like a low-rank density matrix, or our state might be nearly pure, or EPR, or something. And we also might have some technical knowledge. We built an experiment, we know what it looks like, or we have some technology and we know more or less how it's supposed to operate. And the question is, how can we use this prior knowledge to help us out? Okay. There's a little bit of a caveat, though, which is that most of the time when we characterize very large quantum systems, we're in the business of doing estimation, which I like to think of as your best guess for what's going on. You take some limited measurements, you fuse that together with some prior knowledge you have, and you sort of do your best guess of what's going on. And here's a whole bunch of examples of that you may be familiar with that are very commonly used. The problem is that we really want to do a certification instead. We want to give you a number, I have this many EBITs, and guarantee that it's not, that you have at least that many. You don't ever overguess. So it's sort of a worst case possibility consistent with your measurements. And this is really important for security and also some foundational issues. So the question is, if we try to exploit prior knowledge to help us, are we always stuck estimating? Or can we use prior knowledge and still have certification? And fortunately, the answer is yes, and I'm going to show you how. So here's how I like to think about it. Assumptions I sort of associate with estimation, and that means that I made some assumptions about my system to help me, and then the answer I get is only correct if my assumptions were correct, and maybe I never know if they were, so I'm stuck with estimation. In contrast, expectations are things I think are probably true, and they may help me make smart measurements, but they're not going to, the result I get is not going to be contingent on those expectations. We're going to find out if we had good expectations or we're asking the right questions. So here's our inequality from before that bounds our EBITs. And we want to go to work on these conditional entropies that we're getting from our measurements. And if we make any approximations or changes or tweaks or whatever, we got to make sure that they never make that number smaller. Fortunately, good news, when you screw around with entropies, or conditional entropies anyway, you tend to make them bigger. So this is another reason why this information theoretic approach is really good, because you can start doing these things and have these guarantees that you're not going to screw up and accidentally tell someone they have more entanglement than they really have. Okay, so we're going to use two of these. The first we're going to use is this. So I had these bold variables that I didn't really explain before, but this position could be some observable in a vector space, right? So maybe it's better to skip to the example. So my position coordinate could actually be an XY coordinate, where X and Y are separate. One is a horizontal variable and one is a vertical variable. So if we wanted to do the quantity on the left, we would have to measure a probability distribution for Alice and Bob in that full four-dimensional space. For every xy coordinate for Alice, we'd have to correlate that with every xy coordinate for Bob. So that's an n to the 4 if there's n measurement outcomes per dimension. It turns out you can just bound this by instead only measuring horizontal correlations separately from vertical correlations. And if you do that, it can only increase your conditional entropy. But if your system was separable, it turns into an equal sign. So if you think your system might be separable or close to it, you can make this approximation and go from, say, an n to the 4 to a 2n squared number of measurements. And it's always true. Even if your expectation was wrong and you have something that's very non-separable, you'll never overestimate the amount of entanglement you have. So the second improvement we're going to do here is exploit the expectation of sparsity. So these pictures should look very similar to the ones you saw from Andy in the last talk. He was talking about time and frequency. Here I'm using position and momentum instead, transverse position and momentum, but they're all equivalent. So if our state is entangled, we're going to expect these distributions to be very sparse. Positive position correlations and momentum anti-correlations. So what do we want to do? We'd like to be able to scan at high resolution in these high joint intensity regions and at very low resolution elsewhere. So we can do many, many fewer measurements. So it turns out that our conditional entropies are going to help us out again. If we have the true joint distribution, we can replace it with a different one where we've arbitrarily coarse-grained it. So that means I can just take a region in here, I'm kind of circling it, and all the elements in that region, I can just replace them with their average value. And if I do that, the new sort of screwy distribution, here's a sort of more sophisticated partitioning you could do. You can only increase your conditional entropy. So that's good. That means we can use that as well. So we put those two things together to make our improved quantitative entanglement witness. It's generalizable to whatever observables you have, but I'm suggestively doing it in X and Y. You'll see why in a minute. So what do we have to measure now? Instead of measuring in this giant space, we separately measure horizontal position correlations, vertical position correlations, horizontal momentum correlations, vertical momentum correlations. We can do it maybe in this partitioned way so there's many fewer measurements than if you were in the whole space. And from that, we can lower bound how many EBITs we have. And the only assumptions in here have to do with how you convert your data into probability distributions. The witness isn't adding any. So that's important. The witness itself doesn't have any assumptions in it at all. It'll work bad if your estimated distributions are poor, but it won't fail. It won't overestimate. Okay, so I have this slide that talk it in here, and the reason I put this in is because we did an experiment, and that's what I'm going to talk about in the last bit of the talk. But when I talk to people in a break or something, I'm the experimentalist, I start talking about the experiment, and then it gets all jumbled in with the witness, and people are confused sometimes about what stuff is just specific to the experiment and what's specific to the witness. This is really our innovation, that we can do this compression and still certify the entanglement. Okay, so we have a paper on the archive that's in review where we used it. How's time? 5 minutes, perfect. Where we have this provocative title that we quantified entanglement in a 68 billion dimensional quantum system. So we quantify 7.1 EBITs between spatially entangled photon pairs, and for each of th12 photons is in a 512 by 512 pixel, so 512 squared local measurement outcomes. And we end up using 20 million times fewer measurements than you would have needed if you used our unimproved inequality, and something like 10 to the 18 fewer measurements than if you tried to do a tomography. So it's a really big improvement. So here's our spatial entanglement test bed. This is what we used to do the experiment. So this is all bulk tabletop optics. So a pump laser pumps a nonlinear crystal with a sort of broad collimated beam, and spontaneous parametric down conversion creates photon pairs. And then we have this apparatus that lets us choose if we either image our crystal onto these DMDs, which I'll describe in a second, or if we go down the image path is here, or we can go down a momentum path, which puts the DMD in the Fourier plane of the nonlinear crystal. So I talked before about asking questions. The questions that we can ask are, where did the two photons come from on the crystal facet? And we expect them to have come from the same place, so that gives position positive correlations. Or we can ask the question, which direction were the photons traveling transverse the optic axis when they left the crystal? And we expect those to be anti-correlated to conserve momentum. So this is a lot like, this is a very close approximation to the regular original EPR paradox. So these DMDs are what gives us our spatial resolution and our detection. They're these arrays of micromirrors. So a projector probably has one in it. So you can sort of individually cause the DMD pixels to point towards a photon counting detector or away. So that lets you select some portion of your local measurement space, and you do it on both sides, and you do coincidence detection to access some rectangular region of the joint distribution you're looking at. Okay, so we want to get these multi-level estimate distributions that are going to approximate our true distribution with very few measurements. So what do we do? So first, here's a picture of the true distribution. This is just a simulation. This is not data. So what we first do is divide the joint space into 4 big quadrants. And you'll see some of them have a lot of joint intensity in them and others don't. And whenever a block exceeds a certain threshold that we set, for us I think it was 0.01% of the total coincidence flux, we split it and do this sort of adaptive quad tree decomposition of our system. So it goes through and it very rapidly gives you a very accurate estimate of the joint distribution with these sort of bundled up regions and gives us what we wanted, right? We wanted to measure at high resolution where these joint intensities were and at low resolution elsewhere. But we didn't have to assume exactly how that was going to work out beforehand. It got adaptively found. So here's a fun little cartoon, or a fun little video rather, of watching it do it. You can see it just extremely quickly figures out where it should scan at high resolution and where it should scan at low resolution. Okay, so here's some actual experimental data. So if you remember back, we need to measure these 4. We're doing both things. We're exploiting the separability aspect, and we're exploiting this multi-level compression. So we have to measure 4 separate distributions: position, position horizontal, position, position vertical, momentum, momentum horizontal, momentum, momentum vertical. That's what these 4 distributions are, and we blew one up. It looks like position, position, X, horizontal, just to show you what this partitioning looks like. And each of these distributions is a 512 by 512 dimensional distribution, so they're big. In total, for all 4 together, we only needed about 6,500 partitions. So that's where this 20 million fewer measurements comes from. And another really interesting thing is that in a lot of these big partitions, they have 1 million pixels in them. So you're getting way fewer than 1 coincidence count per pixel. But the signal-to-noise ratio is high because you're bundling them all up, and maybe you measured 1,000 coincidences or 100 coincidences or something like that. That error gets spread across all of those and helps you out. Okay, so how many EBITs did we certify? You can see that here. This is just, the x-axis here is just as we run the experiment longer. Early on in the experiment, you just haven't counted enough coincidences to have statistical significance, but it levels off. So we did sort of 2 situations. We did with accidental subtraction or background subtraction, we were able to certify or quantify, I guess. It probably shouldn't call it certification if we subtracted accidentals. But we got 7 EBITs, which we believe is the record right now. And also, without any background subtraction at all, we certified 3.4 EBITs. And again, only about 6,500 measurements. Here's some more results that show what happened as you increase your discretization dimension. So we don't have to go to 512 by 512. We could just go to 32 by 32 or 64 by 64 and so on and so forth. And if you to go to the next higher one, it's a progressive measurement. You can, if you go to 64 by 64 or 32 by 32 with very few measurements, you can say, yes, I have entanglement, or no, I don't. And then you can just keep going to figure out about how many you have. One thing I want to point out is there are error bars on here, and our error bars can be obtained just through regular old propagation of error through your algebra. We also, at the request of reviewers, did Monte Carlo simulations of our error to confirm that, and they matched really well. So no numerical inversion or optimization codes, just simple statistics. Full disclosure, though, we do make some assumptions just in this demo. We are post-selecting on coincidences. You saw the background subtraction. We have finite quantum efficiency detectors, but that's not our witness's fault. So I'm going to just skip to the end now in the interest of time, but it's worth pointing out other people are doing this as well, and in the future, what we have a few different things we want to do. We want to demonstrate this in the integrated photonic circuits. We want to think about a resource-based analysis, so instead of asking about how many measurements do we need, we ask about how many copies of our quantum system do we need. We think when you consider bundling up all those pixels, it's going to be even better. Use some multi-channel detection like the photon counting cameras we've seen, and think about other ways to use our prior knowledge. So with that, I'll thank you for listening.
Hi, I have two questions, one on the theory and one on the experiment. Let's do the experiment one first. So you have your data acquisition time curve, and since you're actually doing certification, I would think that early on when you don't have good statistics, you wouldn't be able to certify anything. So I would have expected you would have started low and then you have gone up rather than the other way.
That is an excellent question. So what happens early on is you find intensity in the correlated region, but you've not had a long enough acquisition time to measure things where sort of off diagonal. Right?
I understand. You don't know that it's suppressed in the other areas yet.
Exactly. So it sort of artificially inflates the number. Does that make sense?
Yeah, that's fine. And my theory question was, your final inequality that you had right before the talk could end here, is it really a minus sign on the second horizontal term? And what breaks the symmetry then?
Is it really a minus sign?
You have plus signs on all the H's except for the first one.
There should be a parentheses there.
Okay,
Yeah,
it's a
okay,
parenthesis
so
around
that's
the
just
whole
a
thing.
typo. Yes, these are all positive, or these are all positive. It's subtracting this total term.
Great.
So that was just
Yeah,
a
that's what I
typo.
would expect. Good.
Question up there.
Again, on the plot where you show how the witness evolves with acquisition time, shouldn't we expect that at the beginning, for short acquisition times, the error bar should be large enough to sort of include the final stable value?
Mm-hmm. So that's also a good question. So what happens at the short acquisition, it's actually the same reason as Paul's question. So at short acquisition times, you end up with, for your statistical error, you just have 0 coincidence counts essentially in all those off-diagonal elements, and thus the statistical error for that just from Poissonian statistics is low. But along that diagonal where you have high photon counts.
So I'm guessing the error analysis sort of fails because you don't know what prior to use or something like that.
Right, so I mean, the error bars just represent the statistical fluctuations, but just the nature of the experiment causes there to be a bias in these early acquisition times. Fortunately, what you can do so that you don't have to be so worried about this is you do a lot of short measurements and you just keep doing them. So when we did the experiment, it wasn't like we sat on each region for 5, 10, 30 seconds. We were doing very short acquisition times and just repeating them. So you'd see it build this curve up, and you'd need to wait till the standard deviation of your mean was to your satisfaction.
Thank you.
Great. Well, actually, in the interest of time, let's move on if we could take the questions after the break. Thanks, Greg.